Hello, my name is Sai Kondapalli and I'm part of MySQL engineering group. Today in this session, I'm going to talk about what Azure Database for MySQL is, how to handle scaling when applications are in a growth spurt, how to handle right scaling using third-party solutions such as Vitess, and finally demo how Vitess can help customers run their mission-critical workloads on Azure Database for MySQL to scale it infinitely amongst multiple MySQL nodes. Before talking about scaling solutions and strategies, let me first introduce by talking briefly about Azure Database for MySQL. Azure Database for MySQL is Azure's platform as a solution or PaaS MySQL service. It fully runs on Community Edition of MySQL, and customers whose workload running today in on-premises or on other cloud providers can fully run on Azure Database for MySQL with little to no changes to their application. It takes away the heavy lifting on customers' end, and customers do not have to worry about tasks such as infrastructure provisioning and maintenance, and also critical DB management tasks such as updates and upgrades to their MySQL versions. Azure Database for MySQL fully integrates with customers' existing tools, frameworks, and drivers so that they can easily migrate from their on-premises environment or other cloud providers to Azure Database for MySQL seamlessly, efficiently, and quickly. It provides customers with maximum control, such as controlling maintenance windows, instance and storage scaling for their application demands and workload needs. Customers can also tweak server level parameters to make MySQL work optimally for their application workloads, and it has built in data security integration such as encryption at rest and encryption in transit, to name a few. Customers who deploy their mission critical workloads can leverage the built-in resiliency to ensure database continuity with features such as same zone or zone redundant HA deployments, as well as building up read replicas in the same region or across regions for read scalability, as well as leveraging the zonal redundant backup option so that customers always have this business continuity and disaster recovery options with Azure Database for MySQL. And Azure Database for MySQL, being part of Azure ecosystem, provides customers the ability to integrate with other Azure services such as AKS, app services, to name a few. And with its pay per usage billing models, customers would only pay for what they are using, and that helps them to reduce their total cost of ownership with built in features for performance, high availability, and security. Today, Azure Database for MySQL is available in couple of deployment choices. So the very first one is the flexible server, which is the latest and greatest deployment choice for customers to run their mission critical MySQL workloads on Azure DB for MySQL. It provides customers with greater flexibility, such as customizing maintenance windows and greater number of server parameter controls to tune the database as per their applications requirements and workload demands. And customers also have flexibility to set required number of IOPS for the DB server so that they do not over provision or under provision. Similar with compute as well, so they can actually pick the right instance size to serve their application. And the other deployment option that customers have today is single server, which is a fully managed MySQL deployment option for customers. And it has built-in high availability capabilities, and it is recommended for customers who are looking to deploy their MySQL databases that do not require full control on maintenance windows and are tolerant to automated patches. Similarly, applications that have minimal requirements for database customizations, as well as that do not depend on zonal redundancy, or good candidates to deploy their applications on single server. Now that you have your database stood up to support your application, let's look at some strategies that customers can leverage for their Azure Database for MySQL when their applications go into overdrive. Let us start by looking at the first option that customers can leverage when they see influx in application requests to their database servers. And now that the database server is getting stressed with this greater number of requests, the very first thing that customers can leverage is basically vertical scaling. wherein this process involves providing more resources to the existing database server nodes. Things such as enhancing the compute power with provisioning of greater number of cores, so you can enhance your server's transactional processing capabilities and greater amount of memory to ensure large data sets can reside in memory to minimize any requests that are frequently going to the storage layer, and also larger networking bandwidth, so greater number of requests can be tackled efficiently in a concurrent manner. And finally, also increase in storage size to handle the rate of data changes and persistence of new data coming in from the application server into the database server. And also more IOPS so that you can reduce the bottlenecks on the storage side. So how does vertically scaling your MySQL database server nodes look like in Azure Database for MySQL PaaS offering, right? So the very first thing that you can do is you can enhance the compute power as well as the memory for your database server nodes. Things such as you can increase your compute from basically from a single core database server to up to 96 cores, which provides greater flexibility for customers to choose the apt instance size to tackle the application and the workload needs. And similarly, as you choose your compute power, you also get to choose the memory for each of these instance sizes that are tied into these particular SKUs that are available in Azure Database for MySQL. And in addition to that, another point to note is that each of these database server instance sizes that you're observing are also directly tied to the maximum IOPS bandwidth that are accommodated through each instance size. For example, if you look at a 2-core 16 GB memory database, the maximum IOPS bandwidth that particular database node can provide is up to 5,000, irrespective of what storage and IOPS you set in the background, right? Because this is the amount of IOPS bandwidth that the database node can handle. Similarly, if you're going to the latest generation of 96 core with 672 GB of memory, you can go up to 48,000 max IOPS, which is the IOPS bandwidth that this particular compute size can offer for customers' workloads. Now let us go in and look at how storage can be scaled as well as IOPS can be scaled up and down based on the application and the workload needs. So in case of Azure Database for MySQL, customers can provision up to 16 terabytes of storage. And as the storage is growing, customers can increase the storage size manually, or also they can set auto grow option for the storage. So if storage is getting filled up because of the application, customers do not really have to take any manual actions or manually intervene to repeatedly increase the storage size. They can set auto grow, and automatically the storage will grow once a threshold has been hit for the base storage size that has been observed earlier. And because of this, it becomes much easier for customers to scale the storage side of things. And also when it comes to the IOPS side of things, depending on the compute size, customers can set up to 20,000 in case of Azure Database for MySQL today. And relatively, some customers do observe that certain patterns can happen for their application. Let's say that you have an e-commerce application, and because of e-commerce, sometimes you may be having marketing campaigns running for your application. So during the marketing campaigns, you can increase the IOPS to maximum so that you do not have any bottlenecks when the application is initiating requests. And once the marketing campaign has ended, to reduce the total cost of ownership, customers can quickly scale down the IOPS based on the application need and the workload that they would observe in a normal peak hours, right? So it gives that additional flexibility for customers to tweak the IOPS up and down depending on the application needs and how their application workload peaks look like. Do they have any sort of patterns that they're observing, and based on that they can tweak them up and down. And so when it comes to vertically scaling a database node, there are certain constraints, right? Because you are completely isolated to, increase the database, compute, memory, storage, and IOPS in a single node. But what about, splitting some responsibilities or introduction of segregation for your application workload, such as separating writes and reads? So in case of Azure Database for MySQL, we currently have the capability of providing read replicas for the existing database nodes that are currently, handling both writes and reads. So what does read replicas do besides the standalone database node that we were discussing earlier, and that was actually going through vertical scaling process when the application growth has been observed, right? So let's say that customers have an application where 70% of their workload is basically reads and the rest 30% are writes, more or less. In those cases, read replicas are an apt solution for customers to leverage so that they can segregate their write workload to a primary node where all the writes will be going, and they can separate out or create another server or servers which can act as read replicas that are asynchronous in nature, and they use MySQL's native binlog replication technology to propagate any writes that are going to the primary server, and all of these writes would propagate to the read replicas in real time, although they are asynchronous in nature, and it's dependent on multiple other factors for the writes to propagate from the primary server to the read replicas. So what advantages and what use cases do read replicas solve for customers in real time? First and foremost, they improve the performance of the application. When customers' applications are more read heavy in nature, they can improve the performance and scale these read intensive workloads by provisioning additional read replicas for the existing primary database servers. So in which case all the read workloads will be hitting the read replicas and write workloads will be hitting the primary database server. And how can customers, provide this segregation of writes and reads between their database servers, right? So customers can build this logic into the application so that, if they observe any DMLs or DDLs coming in from their side, from their application side, those will be directly hitting the primary database server. And any select statements or any analytical queries coming from the business side of things, they can actually set up the endpoints in a way that they actually hit the read replicas. If customers do not have that capability to introduce that application side logic to automatically tackle the separation of writes and reads, they can also leverage other third-party lightweight connection proxies such as proxy SQL. So proxy SQL can automatically take care of that segregation of writes and reads between the primary server and the read replicas, and more or less use read replicas for your read scaling as well as for any business intelligence or analytical reporting for customers applications. And some other use cases such as in internet of things or any manufacturing scenarios, normally your telemetry will be ingested directly to the source database server, and obviously you can leverage the multiple read replicas that you can provision to hit your reporting servers, which are read replicas in nature. And in case of Azure Database for MySQL, customers can provision up to 10 read replicas per primary server database node to handle the scaling challenges and also the different use cases that they have from a read point of view, such as from the business side of things, any business intelligence or analytical reporting, as well as from the application side for read scalability in an availability zone, across availability zones in a region, or as well as across regions for read scalability of the application. Now let us look at some of the considerations, best practices around read replicas for Azure Database for MySQL. So today read replicas are only available for certain compute tiers in case of Azure Database for MySQL, such as general purpose and memory optimized in case of single server, and business critical in case of flexible server compute tiers. And since replicas are just like any other database server nodes, except in the responsibility that they are only there for read-only workloads, they are considered as new servers, and you manage them just like any other MySQL database server. And when you create a read replica from a standalone primary server, primary Azure database for MySQL server, they are created with the same server configuration as the source database server, and you can tweak or change any of these configurations or server properties after the creation of read replica, such as the instance size, the storage size, as well as the provisioning of IOPS, etc. Right? So all of these can be changed after the read replica has been created. And since these read replicas are acting as just like any other standalone MySQL database servers, you will incur billing charges for each read replica that you provision. And the billing is computed in terms of virtual cores as well as the storage in GB per month. And to monitor the replication lag between the primary or the source database server and the read replicas, since as I mentioned that the replication topology that read replicas take into consideration is the native MySQL replication topology, which is asynchronous in nature, we have monitoring that is built around read replicas, so that you can monitor a specific metric, a replication lag, which is in seconds, to understand how much in seconds duration the read replica may be lagging behind the primary server. So these capabilities are also provided. So it provides you with decision choices, such as supposedly if a disaster strikes your primary server and you would have to promote one of the read replicas, you can promote them by stopping replication. And when you stop the replication, the read replica will now become its own standalone database server that can process both writes and reads, and it is now not a part of the replication topology as it was before the promotion of this database server to a standalone database server. So far we have discussed vertical scaling, which can tackle an application's growth to a certain extent, and it is more or less constrained by the hardware that is available to tackle the application and the workload needs. And similarly, we did also look at read replicas, which are more or less addressing the read scalability needs of an application. But what about improving scalability and providing efficiency for the transactions where the application is a lot heavier on the right side of things rather than read? That's where we'll be talking more about sharding as well as partitioning of data today. And before we talk about one aspect of partitioning, let's think about why you have to partition data, right? So first and foremost is improving the scalability of your systems. So for instance, when you scale a single database system, obviously it is going to hit a physical hardware limit. But if you divide the data across multiple partitions or multiple shards, each hosted on separate hardware themselves, then you can scale up the system indefinitely, right? And the other thing is that you can also improve performance of your systems, such as providing separation to divide larger data sets into smaller data sets. And when this is done correctly, you can make your system much more efficient. And also operational flexibility, such as things such as maintenance that can be performed on certain parts of the application than taking down the whole application for maintenance. And sometimes to also match the pattern of data usage depending on which parts of the application are going to use it, and based on that you can perform partitioning of your data. And finally, the other thing is that you can increase the availability, as in instead of your entire application going down, if something were to go wrong, only parts of your application could be impacted, which would minimize the customer sentiment, negative customer sentiment as well. So one of the partitioning scenarios that we can look at is the functional partitioning of data, which is more or less like, where you are separating a large monolith of data into multiple database nodes where you are going to store data as per different categories or types of data. For example, take an e-commerce application that has order related data, customer related data, as well as the products that are being listed on the e-commerce website. And if you separate them into three separate systems or three separate database nodes, you can scale your application for improving the right scalability and also improving the performance of your each of these database nodes. And operational flexibility would also be easier, as we just discussed earlier, and also it would improve availability of the entire application as a whole. But what are some issues, right? So after an extent, it kind of becomes too complex for you because the scalability is again limited over here. And should there be any queries that have to fan out between multiple parts of the application, like, you want to tie in the customer related data with the order related data, then the latencies could increase and can cause, negative customer sentiment as well. So let's look at how slicing the data for an unsharded database across multiple shards look like. So let's say that, currently you have an uncharted monolith database who also has read replicas, right? Now you can actually partition that into multiple shards with each of their own read replicas. So this provides you with a couple of things. As your data set is growing, you are basically breaking down this large data set into multiple smaller data sets. So that becomes easier for you to handle your read workloads as well as your write workloads coming in from the application. However, customers are still responsible for designing their application in a way to introduce the application side logic so that all of these transactions that are coming in from different parts of the application are actually hitting the right shards. And any cross-shard queries that are to be handled by the application should also be built into the application side logic. What this does is introduces additional complexity and sometimes a bad experience for customers who have to wait for these cross-shard queries that have to be computed and the result set have to be sent back to the end users at some point. And what other things do functional partitioning can introduce as complexity is that, of course, if you have like two shards or three shards, it is very easy to manage. But let's say that, there are like 15 shards or 20 shards that are associated with the application. At some point, it becomes an operational burden because you cannot manage every part of it. The reason being, if one of the primary goes down, then obviously it introduces additional complexity of bringing that part of the application. So the DR implementation becomes a complex scenario here with functional partitioning, where you slice your data across multiple shards. Now let us look at a ready-made tailored solution that a lot of the MySQL's large customers are currently leveraging today, and we'll start by introducing what Vitess is. So let me introduce you to by talking a little bit about Vitess. So what Vitess is, it is basically a middleware solution that can sit in between your application server as well as the database server nodes, right? So, and you can run Vitess in multiple platforms, like you can deploy Vitess as a middleware solution on your virtual machines as well as on Kubernetes. So in case of Azure, we can leverage Azure Kubernetes services for that. So all in all, Vitess is a database solution for deploying, scaling, and managing large clusters of MySQL database instances. And it currently supports MySQL and Percona Server, which is a different flavor of MySQL. And it is architected to run effectively in customers on premises as well as in public and private cloud architectures. And it combines and extends many important features of MySQL, and it provides the scalability of a NoSQL database at the end of the day. So how it functions and appears to the application is basically as a single monolith. Even though you have horizontally partitioned your data to sit across multiple database nodes, it can give the illusion of, as a single monolith database to the application, which means it would minimize any application level changes to a very minimum when you implement Vitess as a sharding solution. And it is very easy for customers to move from like an unsharded large database to a sharded architecture using Vitess. And Vitess provides customers with a bunch of other features as well, such as, it can provide you with query routing capabilities, as in it can identify which query should go to which shard and get the appropriate result sent back. Similarly, for write capabilities as well, it will make sure that, the record that is coming in from the application for a DML is actually hitting the right shard to where it is supposed to sit based on the partitioning scheme that you specify. And it can do resharding, so there are other sharding capabilities as well. Of course, customers are still responsible for identifying the right sharding keys for the application. That is to identify parts of the application and parts of the schema that customers think that, are right candidates to be sharded upon, and that is where, the partitioning keys come into picture from a customer point of view. And Vitess is compliant with JDBC and Go database drivers, and it implements the same MySQL Server protocol, which is compatible with virtually any language that your application is written in. So at the end of the day, transactions will still continue to remain ACID compliant, just as how MySQL supports it. And Vitess, when it originated in 2010, was actually part of YouTube, and YouTube were running these large, massive MySQL clusters, and they were hitting these scalability issues. And because of operational burden, they came up with the solution. And the solution today is Vitess, which is an open source third-party solution for sharding capabilities. And since 2018, it's part of the Cloud Native Foundation, and customers such as GitHub, YouTube, Pinterest, Square, as well as Twitter, Uber, Airbnb, to name a few, are some of the largest MySQL usage customers that are currently leveraging Vitess for their sharding capabilities and also to enhance the write scalability of their application. And let us also take a look at some of the important components that make Vitess work appropriately. And in the next few slides, I'll be touching upon components such as VT-Gate, VT-Tablet, Topology Server, VT-CTL, and VT-CTLD, as well as vSchema, and how these components kind of, work and what their main usage is and why they are so critical in case of Vitess. So first, let's look at VT-Gate. VT-Gate is a built-in lightweight proxy on the Vitess side, and it provides abstracted view to the application. So VT-Gate is more or less like a proxy where your application servers can directly interact with, and VT-Gate is the one that is responsible for, talking to the backend nodes through another process, which we will come to in the next slide. And VT-Gate has interesting capabilities, such as it can consider the sharding scheme and can route queries appropriately. For example, let's say that you have horizontally sharded your customer data to sit across multiple database nodes, and you would like to know a set of customers who have signed up for your application in the last 6 months. And VT-Gate is aware of such capabilities, and let's say that you have sharded this data based on a hash key. VT-Gate can take that into computation and ensure that the query that is coming from the application is actually hitting the right shard. So it can consider the sharding scheme, and also, let's say that you have queries that are coming in from the application that have to span multiple shards. And of course, these result sets that are coming from multiple shards have to be tied together and sent back to the application or the client. And VT Gate can do that. It can consolidate the result sets from multiple shards, and it can send that back as a single result set to the application. So all in all, it provides that great abstracted view to the application by itself. So the application does not have to worry about any other application side code change logic. So you can simply implement VTGate in between through VTES, and VTGate kind of takes care of everything. In the other component that I was alluding to in the previous slide, where VT-Gate interacts with, is VT tablet. So what VT tablet is an instance of a MySQL node. So you have multiple shards, and multiple shards will have multiple MySQL daemons running there. So VT tablet is the one that interfaces with these multiple MySQL daemons on each of the MySQL database nodes, and it interacts directly with the VT Gate to provide that abstracted view to the application. And there are two modes for running VT tablet. One is a managed tablet mode, and another one is the unmanaged tablet mode. So a managed tablet mode is more or less like, you are not leveraging any PaaS service, but you are deploying everything by yourself in your on premises or even on virtual machines, where the VT tablet can itself be the MySQL server as well. So that's the managed tablet mode of VT tablet. What is an unmanaged tablet? So in case of unmanaged tablet, we are talking about PaaS services such as Azure Database for MySQL, and over here VT tablet would simply be a process that is continuously interfacing with Azure Database for MySQL for persistence of data, as well as fetching of the result set back from the Azure Database for MySQL to the VT Gate. And at the end of the day, VT Gate that we have discussed in the earlier slide can also act as a caching layer, where some of the queries that are frequently being run from the application to the tablets can be saved there. So that can minimize the round trips coming in from VT Gate to the VT tablet and to the database layer. So more or less, it's like a sidecar to your database nodes if you think about VT tablet, which directly interacts with the server. So in our case, it will be interfacing with the MySQL nodes, which are used for persistent storage. And the other capabilities that VT tablet has, or more or less, it can perform health checks along with topology service, which we will come to shortly in the next slide, to ensure that the backend nodes are healthy. So what's a topology server? So we were just discussing about VT tablet and how VT tablet can do this health checks with the backend database nodes to ensure they are healthy. And when the queries are coming in from the application to the VT Gate and then to the VT tablet and to the MySQL database server, it kind of the VT tablet kind of ensures that the backend databases are healthy by repeatedly running this health check commands that go against there. And all of these health check commands are basically managed through a topology service. And in case of VTES, we call that a topology server. So what's a topology server? So it's basically a key value store that stores metadata information pertinent to the VTES cluster. Things such as your configuration information for the VTES cluster, that includes key spaces, shards, what shards are there, and what the sharding partitioning scheme kind of looks like, and what the tablets are, that health checks that are run on the tablets, and if the tablets are healthy or not. All of these details can be stored through the topology service, which is more or less like a key value metadata information store. And with all of these components inside VTES, you also need a way to track what is happening and also to perform any admin actions on VTES cluster. And that is where VTCTL and VTCTLD come into picture. So VTCTL is a command line tool used to administer a VTES cluster. and it is available as a standalone tool that customers can directly query and interact. And I'll walk you through that in our demo as we progress through this session. And some of the commands as simple as, like the client server, and list out all the tablets for this particular Vitess cluster that are associated with this Vitess cluster. You can perform such commands and understand if anything is out of order, and you can take actions on that. And using VTCTL, you can identify things such as what the primary databases are, what the read replicas look like, and also you can create tables through VTCTL that can be distributed amongst these database nodes. And you can perform resharding operations and so forth using VTCTL. And coming to VTCTL is more or less like an extension of VTCTL, but it's a HTTP server that lets you browse information in a graphical user interface format. And I'll also walk you through that in our demo as we progress through the session. And that's how it looks like. It provides things such as, key spaces, which are more or less treated like schemas in case of MySQL, and they show details such as, how many shards are underneath each of these databases, etc., and what the topology look like. And admins can simply log in and browse through this to gauge the information or gather additional metadata pertaining to the Vitess cluster. And finally, one of the logical things that we can talk about in Vitess is the vSchema. So vSchema more or less provides an abstraction view, and it presents all the key spaces and shards as a unified view for VTGate and the application. So let's consider a simple schema, right? Like a customer schema, and this customer schema is currently sharded to sit amongst couple of database nodes, and that has been partitioned using a hash algorithm, and it kind of lists out which column in the table has been used for partitioning the data horizontally amongst multiple database nodes. And it also gives enough information for VTGate to take information such as, any application queries that contain a where clause can, leverage vSchema to route the query to the appropriate shard, as we were discussing earlier. And before we dive into the demo side of things, this is the implemented architecture that we are going to walk through. So as you can see in the middle, we are running Vitess on Kubernetes, Azure Kubernetes Service, and these are all the components that I have just walked you through, like the VTGate, the VTCTL, VTCTLD, which are the admin client tools, and then topology server to track the tablets, the health, the shards, the schemas, etc. For this Vitess cluster. And of course, your application can run on a virtual machine, it can run on a Kubernetes cluster or an app service or even Azure functions, right? So it can be anywhere, and it's going to interact with Vitess that's sitting on Kubernetes or even on a virtual machine, depending on how available you want your Vitess cluster to be, as well as how easy you want to manage all of these components inside Vitess. In which case, Vitess is built aptly for Kubernetes, so we strongly recommend that you run Vitess on Kubernetes. And as you can see, there are multiple shards for us today. All of these shards are Azure Database for MySQL, and these shards are directly interacting with VT tablets over here. And the VT tablets in turn talk to the VT gate to take any commands or requests that are coming in from the application that is hitting the VT gate. Let us go ahead and spend few minutes looking at the Vitess implementation amongst couple of Azure Database for MySQL flexible server nodes, and how that makes things a lot easier, and how VTGate can actually send the data to appropriate node for a write command. We'll see how the data is going to progress in the next couple of minutes. Now let us look at my resource group. So this is my resource group where I am currently where I have currently deployed a couple of Azure Database for MySQL flexible server nodes, and another virtual machine, more or less, that is being used to connect to my Kubernetes cluster where the actual Vitess cluster is running and all of the Vitess components are deployed in different pods. So let's go to command line client and run few commands to get through this. So I'm currently connected to my Azure virtual machine, which is kind of interfacing with the uh, AKS cluster where we have installed our Vitess cluster. As you can see, there are multiple pods on which Vitess is currently running, and there are like a couple of tablets. There is VTCTLD component, the VT gate, and then also finally Vitess operator, which is actually the one that kind of manages all the components of Vitess inside Kubernetes. So now let's go ahead and run a couple of commands to look at the tablet configuration here. And since we are using unmanaged tablet of Azure Database MySQL Flexible Server, this is what the tablet details kind of look like. So the main thing is that we are connecting to both of these on tablet 2 and tablet 1, which are Azure MySQL based databases. And today we are going to run a demo on a schema called customer schema. So let's look at the metadata related to customer schema. So if I just scroll up over here, you can see that this particular schema is sharded, which means that any tables under this particular schema could pretty much live on multiple MySQL nodes. As you can see, there are like a couple of tables, C order and customer table, who have a couple of indexes which we are using to partition them across multiple MySQL nodes. Now let me connect to the MySQL VT gateway, which is the one that applications would usually be seeing. So let me get in here and then uh, try to connect to the customer database and then do select star on one of the tables where we'll try to insert one record, and we'll see if that particular record is getting inserted in both the tablets or just one tablet. So in the meanwhile, let me also connect to the other tablets. So in case of Azure MySQL, all the databases and schemas that are being managed by Vitess would proceed with VT underscore, and that's how we can see them in the metadata dictionary of MySQL as well. And similarly, let me also connect to the second tablet. Similarly, I'll do the same thing over here, which is to connect to the customer database and then do a select star on the C order table. As you can see, there are like 3 records in tablet 2, and in tablet 1 we have like about 6 records, I would say. So in total we have 9 records, and if we go back to the gateway of Vitess, we can see that there are total of 9 records. Now let us go ahead and try to insert one record from the VT gateway, which based on the hash partitioning scheme should obviously put this particular record into one of the 2 tablets. So I just inserted the record over here. Now let us go ahead and check on tablet 1 first. So let me rerun the query again. I should be seeing the same records that were present earlier. So let's now quickly go to tablet 2 and try to run the select command again to see that this particular record is now only going to the shard based on the hash key. As you can see, we have the newly inserted record over here. And similarly on VTGate side, we can also do one thing which is you can use hexadecimal configuration of the sharded key with the database name. Connect to that, and you can also do select star from C order here, which should only show details from tablet 1. And similarly, you can do the same thing for tablet 2 as well, which would logically show only data related to tablet 2 here. So this is how Vitess can, move the records that are pertinent to the right tablet or the right shard, so that when your application is trying to insert records based on a particular um, partitioning key, then those would be propagating to that tablet. Similarly, you can also perform cross-join queries, etc. And with VTCTLD, you can also do another thing, which is to look at the control panel over here. As you can see, I have a bunch of schemas and key spaces that I have added over here. And the one that we were just working on, customer, has like two shards. Minus 80 and 80 minus, which we kind of logically queried a while ago to see those queries. Similarly, you can go to topology, look at the key spaces, etc., and all of the pertinent metadata information can also be fetched from GUI besides the command line client we just used over here. And that concludes the end of my demo here, to show that we can make Vitess work with multiple MySQL flexible server nodes and use the partitioning scheme to actually make the records present in the right shard. I would like to thank each and every one of you for taking the time to attend this session, to listen into the scaling capabilities of Azure Database for MySQL using Vitess as a third-party solution and a middleware solution. And before we end today's session, I would like you to refer to the following links to our service homepage, documentation, as well as beginner series videos to get started with Azure Database for MySQL. And for any questions related to the service or MySQL in general, please leverage the email channel that we have listed here. And do follow us on Twitter as well as LinkedIn, where we announce updates and any product related innovation that is going in, and any new features that are coming out as well. And for other sessions related to Azure Database for MySQL in this year's DBS Summit, we have put together this information that you can use to attend other sessions as well. And with that, I would like to again thank each and every one of you for taking your time and attending today's session. Thank you, and have a good rest of the day. Bye.